317.
Nice. Thank you. Okay, so 5.15. The radius r of a perfectly conducting metal loop situated in the xy plane increases at a rate of pi r.
Hold on, we got a loop, right?
Yes.
XY, let me just do this. XY, then we got a radius. I'll call it rho, actually, rho. And rho increases at a rate what?
Pi r to the negative first.
So d rho dr, or I'm sorry, d rho dt equals, say again, what was it?
1 over pi r.
D rho dt increases is?
It increases at a rate of pi r to the negative first. Yeah.
All right.
Yeah.
All right, so that's the radial change. Okay, what's the question?
There's a small break
Yeah.
in the loop that has a 2 ohm resistor.
It's not a problem, okay.
And meanwhile, there is a magnetic field going out of the pits, plus z direction. Plus z direction.
So we got a magnetic field coming out, and is it static? Where's the B field?
It is static. It is 1 Tesla.
1 Weber per meter squared in the AC direction. Okay, go ahead. What's the voltage per current?
Current and direction. Magnitude and direction of current.
I call this R. All right, now this is an odd one. So he gives you a rate of increase with respect to time of the radius of the loop.
Yes.
But does he give you the radius at t equals 0 or something?
No. That's everything.
That's all I give you.
Let me just tell you what this guy's, or what Dr. Wentworth's thinking here. He knows the flux through that loop, magnetic flux through the loop, is really going to be the area of the loop, which is pi r squared times the B field. Now, I'm not even bothering with integrations because these things do not vary spatially. So it's equal to pi r squared times the B field. I'll call it V naught. The area of the loop is perpendicular, the surface area is perpendicular to the actual geometric area, and the B field's in the AZ. Does everybody agree with that?
Yes.
Now we know that this, the time derivative of the magnetic field with a negative sign, is VEMF. Y'all with me on this?
Yep.
With me? All right, so if you take minus the time derivative of this pi can come out in front, B naught can come out in front. Then I have ddt of r squared. I'm just showing you, right?
Yes.
All right, the derivative of this is going to be equal to minus pi B naught, whatever it is. Then we take a derivative with respect to t of this. This is 2 times r. And then we have dr dt. Dr dt, he gives this as 1 over r. So this is 1 over r with a pi. 1 over pi r. So he gives us dr dt. Do y'all follow me on this?
Is that chain? That's chain rule.
Anytime you take a derivative, any function, if you take a derivative of any, I don't know if you call it chain rule, any function at all, call it x, then n power with respect to x. That's n times f of, and then it would be x of n minus 1, and then you have to take df of x, dx here. Right? I mean, I think you know this. This is basic differential calculus, right? If you have a derivative of a function to a power, you take the power out in front, then you take the functional form to the n minus 1, and then you take the derivative. You all with me on this, guys?
Yeah.
So this, you can see one thing, Whitworth crafted this, so the pi's go, and the r's go, and you get 2b, or not the b. So what is b again? 1 Weber per meter squared. So this is minus 2, really, and this now is going to be volts per meter. volts per meter, I'm sorry, volts, pardon me, minus 2 volts. And you'll notice it's going to be such that this voltage, which is VEMF, is negative minus 2 volts. Does everybody follow me on this, how I got this? So I'm going to switch the polarities. So it's actually this. It's going to be, that was plus on top, now negative to plus, if it was a gap. I want to just do this way so you don't get confused. That would be the voltage that would be developed. Does everybody follow me?
Yes.
I want to make sure you see this next part. Is that right, by the way?
Yeah. I remember seeing it, yes.
For the voltage.
Yes.
Volts?
I remember the current was 1 amp, and that's just...
We're going to get it in 1 second.
Yeah.
Right, now, what direction is the current flowing? Take a look at this. The actual the electric field is forcing plus charge here, right? And minus charge here, right? It's trying to force things around. So when we actually put the resistor here, current's going to flow that way. And the current's going to be 2 over 2, or 1 amp, but it's going this way. Y'all with me, class?
Yes.
Is that what he has?
Yes, it's 1 amp clockwise. Yep.
All right. Y'all following the method? By the way, I don't like that problem. Loops just don't grow like that. I mean,
it's opposite the B field, right?
well,
Opposite
you
of
don't
the
care
induced
about the
current,
direction of the B
current,
field.
or the induced current. You don't care about that?
No. The B field, because the B field could be kind of good. The thing you worry about is this. You'd have to find the flux through the loop. In this case, it's just B times that, because the B field's aligned with the differential area. Then you got to take a time derivative of that and put a minus on it. That gives you the direction of voltage, which will give you the direction of the electric field driving stuff.
But isn't our induced current is opposing the change in flux,
the B field.
the change in the flux, and so
If it was a change, yeah. Well, if this is Lenz's law. Now I'm going to show you that Lenz's law doesn't work for something that's opening up like that very well.
Okay.
You can make a case for it, but it's very. I'll talk about that later. I wouldn't mess with it. Just do it that way. I don't. That's. Go ahead.
no, I'm trying to I'm doing right hand rule and trying to make everything mesh well in my
Well, all right, go ahead. By the way, sometimes when I give exams, the right-hand rules being used, I will see people. It's really like they're dancing some weird. It doesn't happen that often, but sometimes, especially when they're.
That's kind of mad, but yeah. Oh, I have I do have one more question, but before that, quiz on Friday with this material?
Yeah.
Okay.
This and the last class. What we covered, which is basically today.
Yeah.
All right. So you got another question for me?
I do.
Thank you for that question. That's a good one. By the way, that's an irritating problem.
I do. I got 5.8.
5.8?
Yeah.
That's an old one, isn't it?
Okay,
Okay.
just signed it last homework.
Yeah, this is current homework.
But go ahead.
It says considering the figure, that's annoying. I gotta find it. Hold up.
Considering the figure.
This one.
Okay, hold
This
on.
figure.
Let me is there just one coil? It's
I think it's a single coil.
There's two.
It says suppose the
Two
area.
coils, sorry.
Yeah, I think it's 2 coils.
all right. Okay.
And then VR. Okay. Suppose the area of a single loop of the pair is 100 centimeters squared, and the magnetic flux density.
0.01.
The magnetic flux is up or down?
The magnetic flux density is constant over the area of the loops, but changes with time as B equals B naught e to the negative xt in the AZ direction.
XT?
X is a constant.
X is
Oh,
a
chi.
it's chi. No, it's 0.3. I don't know
Chi
why.
is 0.3?
Yeah, it's 0.3.
Okay.
And then B naught is also 4 milliwebers per meter squared.
All right, N is 2, and so this is 4 milliwebers
Yeah.
times 10 to the minus third, and this is going to be e to the minus xt webers per meter squared. Go ahead.
It says determine VR at 1, 10, and 100 seconds.
Oh, and this is connected to a small loop with a resistor, a square root loop with resistor. But
Inside.
it's vertical
All right, let's work a resist. I'm just going to do it this way. What's the value of resistor?
Yeah, that works. I don't know if it gives it that. Let's see.
We don't get that.
It's just the voltage R is cross resistance.
All right.
But it, once defined at 1 second, at 10, and then at 100 seconds.
All right, here's what I'm going to do. I'm going to make that loop in the plane here. I'm going to call this X, Y. Here's my loop. It's got 2 turns, but I'm going to show you this like this. Basically 2 turns, right? Got an area here of 100 centimeters squared. So that's, for meter squared, centimeters squared is going to be 10 to the minus 4th meter squared. So that's really 10 to the minus 2 meters squared, right?
Yep.
Meters squared here. Now I got a B field coming out of the board, and the B, if this is X, Y, Z's out of the board, and it's, this is going to be coming out of the board, and I'll get out of your way for it in a second. So this B field coming out is actually equal to 4 times 10 to the minus 3rd. That's going to be E to the minus, I'm just going to call it chi. I don't like chi, but chi t. And it's really U of t. It's only for t greater than 0. What it doesn't assume this thing's got values for t less than 0. And he wants this voltage. Now I'm going to try to do this where I'm going to break this loop right here. Here's the voltage, and we'll call it V of R. Now, again, I don't know which part of the loops he's got going first to the resistor, but I'm showing you how it would be in the XY plane. You all with me, class? So the next thing what I'm going to do is first, I'm going to calculate the magnetic flux through the loop. I'll call it the flux linkage. So that's equal to the number of turns, right, times the magnetic flux through the loop. And that is 2 turns, right?
Yep.
And then the magnetic flux through the loop doesn't vary spatially, so it's just this B field times the area. And that's Webers per meter squared, right?
Yep.
All right, so that's going to be 4. I'm just going to go ahead and do this. He gave me the area, right? So it's just the area times the B field, so it's 4 times 10 to the minus 5th. You all follow me? I'm just taking 10 to the minus 2 times 4 times 10 to the minus 3. And it's going to be E to the minus, I'm going to leave it as chi for now, chi t. That's the magnetic flux. Now to find the voltage, I have to take a time derivative of that, right? Throw a negative sign in front of it. So to get VEMF, and the direction shown, I take minus d dt of that. And that's going to be what? That's 8 times 10 to the minus 5th, or 80 times 10 to the minus 6. Then I have to take a derivative of this, which brings out, it's minus that, a minus chi times e to the minus chi times t. So that means the actual VEMF shown here, this will be the EMF, is positive on top. So that's going to actually be, the 2 negatives cancel, and I get 80 times 10 to the minus 6. Chi is, this chi, 0.3, right? 0.3, or 3 times 10 to the minus 1. And then it's times e to the minus 0.3 t. And that's the general equation. And they ask it for what times again?
1, 10, and 100.
Let's get it for 1. Obviously, the only thing that's going to change is this. So VEMF for t equal 1 is going to be 1. This is 3 times 10 to the minus 1. So that's 240, right? Times 10 to the minus 7, e to the minus, and it's 0.3 in 1 second, did you say?
Yep.
All right, so it's 0.3. I don't, e to the minus 0.3, I don't know what that is, but you can tell me.
It's 17.8 microvolts.
Is that right?
Yes. I referenced the book, it's very different.
Are you all with me? All right, now, these problems are not tough. They just require a little bookkeeping skill, because sometimes you get bored doing them. Most of the method to do it is obvious, but I'll tell you where you get really messed up. You get careless with like chi and stuff like that. I promise you, people get really careless on quizzes and tests. You got to be attentive to detail and don't get too wired up about it. But Try to make sure you keep it straight in your head. Okay, next one. That's not a bad problem. It's not a great problem, but not bad.
I'm fine.
Oh, I got another one. We can do.
Hold on, let me get this. In my opinion, by the way, I teach differently than a lot of people. I don't like PowerPoints. I'll use them if I have to. But I think the real learning comes after you get some basic theory and then you struggle through the problems and they're done. I've always found that whenever, especially when there's a lot of things you can stumble on, a person works through the problem piece by piece. And you know, I'm teaching random. Random's got some really wild stuff. I don't teach random often. A lot of it is sort of very abstract, in my opinion. He's in my random class, so are you. But you know, these problems, like, this is physical electromagnetic problems that these are right down. This is what I did my PhD. I live in that world. What's the next one?
513. It's got a figure as well, but it's just it's a simple figure. It's just it's an infinite line of current in the z-axis.
Okay, hold on. All right, so this is the z-axis, and we got I of t.
And it's got a conductive bar of height 2 centimeters moving towards the z-axis.
Moving towards it.
Yeah, moving towards it.
All right. So we got some velocity, right?
The velocity is -1 a rho meters per second.
-1, what? Meters per second?
Yeah, meters per second.
1 meters per second. I'll call it a rho. It's just going this way.
Yeah, it's just going towards it.
And it's 2 centimeters. That's all. Or 2 meters.
2 centimeters h, and it says towards an infinite length line, the current on the line is 4 amps. And it says find the expression for the voltage from one end of the bar to the other when rho reaches 10 centimeters.
Okay.
So when it's 10 centimeters away.
It's not going to be hard. All right. Now, do y'all agree that from this we can get the B field as a function of rho?
Yep.
All right, so we're going to get it. So the B field is a function of rho, right? It's going to be equal to some, and I'll just call it I of t. Does it give you a value for I of t or not?
It's 4. 4 amps, yeah.
Constant?
Yep.
Oh boy, this is a goodie. So that's 4. This is 4, it's mu naught times 4 over 2 pi, and then it's rho. And this is really into the board. I'm just going to call it a phi. It won't be a problem, all right?
Yeah.
Now, next, I know that if you have anything moving, any bar at all moving in an electric field or in a B field, that you get an induced electric field, and the induced electric field, I call it EMF, it doesn't really matter, it's motional in this case, is just V cross B. Y'all remember me doing that?
Yes.
Mm-hmm. That'll give you the direction of the charge will accumulate, and you can get the voltage from that. When I take a look at this, velocity is this way. Just do it with me. All right, V is that way, right? V cross B, electric field down. Y'all see that? So the electric field is down, and the value of the electric field is going to be equal to V cross B and V. So this is actually, it's going to be in the minus E direction. I'll just call it minus AZ. And then it's going to be 1, right? It's 1 times that, so it's really 1 times mu 0 4 over 2 pi rho, and that's it. Y'all follow me? All right, you got to multiply. That's the E field. They want the voltage. Is that right?
Yes.
All right, so I multiply it by the length. So I just take this right here, and if I multiply this by the length, remember it's going to be plus down here, minus here, and the length was 2 centimeters. Then I get the voltage. So what does this look like? The actual voltage, V plus down here, and I'll call it just plus minus, is going to be equal to mu 0. Mu 0 is 4 pi times 10 to the minus 7 times 4. I'm right here. That's the current times 2 centimeters is 2 times 10 to the minus 2 over 2 pi here. And they want it for rho equal what?
10 centimeters.
10 centimeters.
So that's just it's 10 to the minus 1. And you can take, I don't know what all that comes to. The 2 pi and 4 pi will give you 2 on top. 2 times 2 is 4 times 4 is 16. Then you got minus 6 minus 2. So we got 16 times 10 to the minus 8, or 1 point, or is that right?
Yes.
What is the answer?
160 nanovolts.
Yeah.
So I have a question about this. So this is the V plus on the bottom because the
Think of it this
electric
way.
field, the induced electric field is upward, and it causes the
Well, the
positive
induced
charges.
electric field is downward.
Oh, it is.
Think about it.
Oh yeah.
It's V cross B. So this is going to be an accumulation of plus charge,
Yeah.
minus charge, right?
So the
If you
E
measured it, what would the voltage be? Plus, minus.
so the E field causes the positive charges to move down the bar, and the negative charges to
Right,
move up.
and this is like, now think about the internals of a battery. When you think about a battery, something inside is separating charge, right?
Yes.
It's an electrochemical potential. It can be viewed as an electric field that's causing that, right? This is the same thing. This would be for like a generator. There would be an internal field, all right, an induced field caused by the V cross B business that would cause charge here and here. Now, outside of here, it's going to cause the discharge path to be this way. All right,
Yes.
that's the only thing you keep in mind. All right, that's not bad. You got another one?
Sure. I can keep going. I have plenty of questions.
I mean, is this answering your question?
Yeah.
His solutions aren't bad, Bubba. He puts a lot of details. You know how the solutions are in random. I have to do a lot of back work. I have to really work up solutions to show just how to get some of these identities that he used in there. This is not bad. His book, by the way, what he does is pretty clear. I don't see any, just really difficult things to try to figure out how he got where he's going. And what he tries to make things obvious. He's a very good teacher. I bet he's retired.
Yeah, we did that yesterday.
Did he used to teach random?
What?
Did he used to teach random, or did he just
No,
tell EMAG?
Stan Reeves was a random guy. He retired. John Hung was controls. He retired. Riggs was an EMAG guy. He retired. What Stu taught mainly was electronics and EMAG. And he taught analog electronics. But you know who he is, at least? He's a fantastic guy. He was considered the best teacher in our department by students all the time.
Huh?
Yeah, it's unfortunate he retired. He's really excellent. Go ahead.
I think all my other questions we've answered in last class.
All right, so I'm going to use your book.
Go ahead.
And I'm going to say, so we did the rho dt plus div j equals 0, and we did the charge decaying and all that crap, right? And then we did induce the magnetic field, and we did transforms, star transforms, right? I want to do the 9 yards on transformers this time for you. He goes through them just basic, but it's kind of important. Now, and he'll have this in his book. So what does a transformer look like? And I like to do it like this. It looks like an iron core, right? And it's got windings like this. Now I want you to just pay attention to this. There's always going to be a primary side, and there's a secondary side. Gross is the guy that can teach this blind. I mean, he teaches it all. And then over here, you're going to have some current I1. And you're going to have a dotted terminal, and this is called V1. And then over here, you're going to have a dotted terminal, and this is called V2, and plus to minus, and there's a current. Now, I2 comes out typically. This is something I don't particularly care for, but they do. They choose this setup. And they're going to say that this has a cross-section A right here. And you don't even have to bother calculating it. And when you think about the reluctance of this thing, they're going to say the reluctance is approaching 0. So there's nothing to limit the flux. All right, that's sort of what they're going for. To tell you more, but this basically you'll get the idea. All the flux is contained in there, right? So the way you normally do this, I think he asked for an equation for impedance, reflected impedance, but I forgot if he does. So I'm just going to do this. Normally what you have to do is first find out what these dots mean. Now are you ready? So here's what, has anybody seen these dotted terminals before?
I have, yes.
All right, when you have dotted terminals, what it's saying is, it's saying that if you have a current entering the dot right here, it will create a magnetic flux that will flow in this direction. So that's essentially what it means. You all with me on this? How do you figure that out? Well, you all got right hands, right? Now just follow me. Assume this current's positive. Go ahead and take your index finger in your right hand, put it in the direction of current, and then grab the bar. Your thumb points in the direction of the flux, okay? Now, if by chance, if you put the current in here, now look, I'm trying to get this way, and the flux was going this way, not coming out, then what you do is take the dot here and put it there. In other words, the way you determine the dot is have current going to any one of these two. Then use your right hand to figure out the direction of flux, all right? Current's spinning this way, you might say. It's going spiraling down. That's the direction of magnetic flux. If it was coming in here, if you look at this, coming in here, you're gonna, I'm trying to do this, then it'll be going this way. Do you all follow me? But the dot's always indicating the terminal where the flux would be positive in this direction towards the dot, from the one side of the transformer to the other. It's coming out. That's all it means. Same there, all right? Now, one other thing about this, though. So when you look at these equations right here, there's a couple. One is that really V1 over V2 is equal to N1 over N2. We did that last time. Do you remember that?
Yes.
All right, so the more turns, the more voltage. Think about this. If you have on the primary side, if you wanted V2, and I say on the secondary side, I got 10,000 turns, there should be N2 here. So I would have, think about this. If I wanted V2, I take V1 and then N2, if I made 10,000 turns, by the way, this is a neon transformer, over the primary of 100, that's 10 squared V1. So the voltage on V2 would be 100 times the voltage on V1. You all with me? This gets important what I'm about to show you. Now next, suppose I had a impedance here. I'm going to call it, he doesn't do this in the book, I'm just going to call it Z load. All right? Now if I take a look at this, I'm not going to do it using a number with 10,000, I'm using N1. I know that V2 here is going to be equal to V1 times N2, right? What about the current I2, the current flowing through this? It's just what? It's going to be, think about this. Well, you could say it's going to be V2 over ZL, right?
Yeah.
But what else is it? Remember, N1, I1 equals N2, I2, right? Do you remember that? All right, so I2 itself is equal to, if you look at this, is equal to N1 over N2, right? Times I1. Does everybody follow me?
Yeah.
All right, so come over here. So it's N1 over N2 I1. Now if I take a ratio of V2 over I1, V2 over I2, that is ZL. Y'all follow me? By definition. That's going to be what? V2 is this, is V1 times N2 over N1, pardon me, it should be over N1, over N1, and then this, I2, is going to be N1 over N2 I1. Now I'm trying to show you the method, right? There's one thing that happens when you notice that the actual ZL right here is equal to, just flip this, it's N2 over N1 squared, right, times V1 over I1, and that is what's called the reflected primary value. Now, just take a look at this for a second. Z primary I'm defining as V1 over I1. Now, here's what it means. If you have a load on the primary, or I mean on the secondary right here, it reflects back and looks at the primary like this. Just listen to me, all right? So I have Z primary, and call this reflected. It's really equivalent, but reflected is going to be equal to N1 over N2 squared times the actual Z load. Now, y'all follow me on this?
This was actually one of the homework problems.
I know.
Oh, okay.
But I wanted to take you through it. They're assuming reluctance goes to infinity. I'll even show you the magnetic circuit coupling thing that you're going to get from Gross and other people in a second. But remember, there's one crazy thing happens. Remember this dot right here, and this current's coming out. This is a big deal here, right? The sign, because you're going to find with magnetic circuits, the current's going in. When they talk about coupled magnetic circuits, I might even do that one. Okay, back to this. You see that Z primary right here is equal to N1 over N2 squared times Z load. And what it means is, if you have a transformer like this, and I'm going to keep it real simple. If you have a resistance, say R1, then you have a voltage source here in the primary, call it V, I'll just call it V source, for lack of a better term here. Suppose this is V source and it's in peak. And then you got a transformer here. This is where they'll show it usually. You're going to see coils here. And they'll have what's called a turns ratio. They'll have 1 to N. Where there'll be N times as many turns on the secondary. Y'all follow me? That's what they usually do. And they're going to have then a load. And I'm going to make it real simple. So I'm going to make this thing a load of, it's going to have J40 plus 20 ohms. And say they want to know the current here, call it I1, and make that the dot, that's the dot. They want the current there, they want the voltage here, they want the current here, the voltage here, and last but not least, maybe the power dissipated in the 20 ohm resistor. Do y'all follow me? Now the way you do a problem like this, you skip right to the bottom line. Let me give you some, we'll do a real problem with numbers in a second. Here's what you do. Has anybody seen this before?
A very slight amount in Digitron.
Never had anything in circuits like this?
No.
No.
Okay. When I teach 3810, it's EEs for non-EEs, we go through all this stuff. And when I used to teach, I haven't taught circuits in 15, 20 years. I'm not sure, there were two sessions of circuits, I think. Now, is it just one class?
There's just one circuits class.
It's just one, yeah.
Okay. Well, they probably threw this into the power areas.
Yeah, they did.
All right. If you look at this, go to the primary side, that's this side, and just replace that transformer's effect in that load with the squared turns ratio, okay? So what happens is, remember, there's 1 to N turns. So I've already got rid of the problem of N1 over N2. So over here, your primary circuit looks like this. Then I still have the resistance R1, right? Now I come over here, and now I go ahead, and I put the equivalent impedance, which is going to be this load divided by N squared. You all with me? So it's going to be that load, which is, I'll go ahead and do the whole problem. Let's make R1 10 ohms. Let's make VS 100 volts at 0 degrees. And let's go through the whole 9 yards, okay? And we'll make N, make N equal 20. Just so we can add a bit more, I guess, It'll help you focus on the real thing, I think. So over here, first I'll draw it up as the variables, and then over here, now I take the load.
Wait, is that 10 an angle of 0? Or 100?
Yeah.
100 angle
Okay,
0.
okay, 10.
I could make it 100, here, 100.
You said
Doesn't
100.
matter. How about just 100 volts? That way you can't volts. All right, now, come over here, and now I take, here I put the ZL value, and I divide it by N squared. That would be the impedance. I'll plug these in a second, and we're gonna get I1 here first, and you can see, I haven't even done the secondary. That's reflected impedance, isn't it, class? Thinking about something, you might as well.
Yeah, I'm thinking, it's sweet.
The load circuit, the impedance will reflect down is 1 over N squared.
No, I'm just wondering if I wrote the formula, like if I derived it wrong. That up there. I think I just did it backwards.
It's always the more turns, higher impedance. Think of it that way. So there's 20 turns on the secondary for 1 turn on this. There's the voltage is going to be 20 times as much.
Yes.
The current is going to be 1/20th. The reflected impedance is going to be 1 over N squared. This is going to have a lower reflected impedance than that side.
So that 20 is a ratio, so it's
that's
20 to
why.
1 basically.
Yeah, 20 to 1.
Okay,
I
gotcha.
wrote that was Z1 and Z2, and then I signed Z2 as primary when it's supposed to be the load. I just did it backwards.
That's all right.
Yeah.
Now, y'all follow me in this? We're going to get I1. So how do we get I1? Well, I1 is straightforward. It's just what? Vs in magnitude. Now, forget the phase for now. Over R1 plus Z load over N squared. Y'all with me? I'm going to plug the values in a second. I don't want to get in your way. Can y'all follow me in this?
Yes.
In square.
All right, so Vs, I made it 100. Let's do it. Now, I made R1 10. And then I made ZL 20 plus J 40. But I've got it divided by N squared. That was 20. That's this divided by 400, right?
Yep.
You're going to see that's dang near 10 amps. But if you do this, what do you get? I got 100. I'll try to do this for you. Over 10. And then I got 20 over 400 is really 2 over 40 is 1/20th. Real part plus J of, and that's going to be 40 over 40, J 1/10. So can you give me magnitude and angle, or I tell you what, just give me real and imaginary parts, fine.
I got 9.95 minus J 0.01.
Amps.
Yep.
Right? Okay.
No, it's just 0.1, it's not 0.01.
Oh, he's right. Yep.
Point
It is
one?
0.1, not 0.0.
All right.
But
Okay, about 10, right? Close to it.
Close enough.
That's the current there. Now, here's where you can do it so many different ways. I want the voltage V1, right?
Yes.
How would you get V1? I'm asking you. Well, we got the current. Figure this
Yes.
through.
And so we can
Current
subtract
times
the,
that.
yes, subtract the
How about we
voltage
take
from
this
the-
voltage minus I times
Yep.
R? Yeah, that's the
That's
easy one. Or you could take that current times this reflected impedance. But since this is strict real and this is strict real, we got the current, why not just say the V primary, which is going to be my V1 here, is going to be equal to 100. It's Vs, right, minus I1 times R1, right? Please make sure you see this. Everybody with me? I don't know where everybody is. We're missing him, we're missing Chase, we're missing that guy, this guy. Goodness. Is it something I said? Anyway, you with me, guys? What is it going to be? So V1 is equal to, I said 100 volts, right? Is 100 minus I1, which is at 9.95 minus J 0.1 times R1, which is 10, right? You can give it to me in real imagine, it's fine. What is it?
0.5 plus J1.
So that's the voltage V1, right? Now, next I'm going to get current I2. How do I get current I2? Remember what? N1, I1 is into I2. The polarity is shown. Are y'all with me, class?
Is it basically just how you go about solving these? Is you basically have two circuits that are related by the number of turns?
And yeah, the reflected impedance.
Okay, gotcha.
You don't even need the reflected impedance, but then you're going to have to solve two simultaneous equations. The reflected impedance makes it easy.
Which one is the reflective impedance?
Impedance, the primary C's. See, out here we got 40 plus, or I mean 20 plus J40, right?
Mhm.
But on this side, it really looks like 20 plus J40 divided by N squared.
And that's the reflective impedance?
Yeah.
Okay.
The time impedance, the primary says C's from the secondary side. This is going to help you in the long run. Wow.
No, I got it. Makes sense.
All right, so what does it come down to? Well, I've got the primary current, right? Right? What's the secondary current? I2. We know it's going to be less because there's more turns, so it's divided I1 by N, right? And I gave you the direction, so what is I1 again? 9.95 minus J 0.1, right?
Yep.
Divided by N, which is
20.
20. So this is going to be small, but we get I1, right?
Mm-hmm.
You mean I2? Yeah.
I mean I2, the secondary current. I don't know what it is, but it's small.
Yeah, it is.
Now, how do you get V2? Two different ways to do it. Take V1 times N, we get V2. Or you could take that, right? That current multiplied by 20 plus J40. It'll be the same thing. Y'all with me? And that's really transformers, ideal transformers in a nutshell. By the way, that works 99.999% of the time for any low frequency transformers. Now, there is some tricks with transformers that you'll get into in power. One is there are things called hysteresis loss, which mean in here, you got magnetic dipoles and stuff. And as this current flips back and forth, the magnetic dipoles can do this. They'll burn up energy, just like a lossy dielectric. So you can get losses in the magnetic material that will, and you got to be careful about this because you can't allow the losses to be such that the transformer is going to heat up to a point where it just catch fire. All right, so you got to be, there's tricks to this that you're going to learn about. But most of the time you don't. Has anybody ever worked with any transformers in your life for anything? You know what a neon transformer is? You know what a neon lights are, right?
Yes.
All right, those outputs on those transformers, it takes about 10,000 volts to light those things, right? So they take wall voltage and they jack it up to 10,000 volts. The problem is now the current becomes very small. And neons sometimes draw some current, so they need big old hefty coils. They're on the primary and secondary. Well, the secondary not so much, but the problem is always losses. We used one to, we wanted to use the 10,000 volts to charge up some capacitors for the railgun. We had to create a full wave rectifier on the secondary that could withstand 10,000 volts of reverse voltage, and that was with some clever diodes.
Wow.
We had to also, when we did this, make sure that because we're going to charge capacitors. In the beginning, a lot of current's drawn as you're charging these capacitors. We had to make sure that the core didn't overheat, and thankfully it didn't. But it was an interesting project. You'll learn about how to implement, I mean, all the things you learn, how it affects the real world project design and stuff like this. That was an experience. Again, so I showed you transformers. I'm going to check one other thing. I know in his book, did that make sense?
Yes.
I'm going to give you some stuff on this. So Faraday's law.
Is there stuff in the book on this, or is this going to be extra?
That's. I mean, he's got a real kind of. He gets you the problem about the reflected impedance, but he doesn't ask a specific one. If I asked you something like this, I would expect you to be able to do it, but I wouldn't just ask you that without giving you some prompts. I'll give you a few prompts.
Yes.
Okay. I don't ever try to ambush
Bonus
people.
Yeah.
So next, what's the next book? Faraday emotional EMF. We did that, right? displacement current density. This is a no-brainer. Right. So, in displacement current density, I'm going to do the problem, but first define it, and you're going to see this is trivial. I want to get into Maxwell's real equations, but I want to try to go through these things sequentially as best I can. I don't always do this, but I think it'll help you. A half hour. You know, I'm kind of surprised they don't cover this kind of stuff in circuits because it's so important.
I don't know, it was not.
Do they do op amps in circuits or not?
No, that's in random. But that's not in random, that's in analog.
I do. I do it in random. I mean, I do it in analog. Listen, I don't do it in random.
Yeah, it's in analog, not random. I said the wrong thing.
So, displacement current. Well, it's displacement current density, then we'll talk about displacement current. This is kind of an obvious thing. So, remember I said that the laws, the real laws, were curl of H is equal to J plus the partial of D with respect to T. And then I had Michael Faraday's law of induction, curl of E is equal to minus D B dt. By the way, these are the point form or differential forms relationship between time-varying magnetic and time-varying electric fields, and they work all the time if you accurately really relate D to J to E to B and so forth in H. All right? Problem is, a lot of times, the mu, for instance, you know how we have, I just go through this. We have B is equal to mu H, right? Well, in a time-varying situation, or if it's transient, or if the B field's value or H field's value is going to vary orders and orders of magnitude, mu will not be a constant. So now, when you do that, all of a sudden, the derivative of this with respect to t is not just mu 0 t. Now you got to take a derivative of mu with respect to t times h plus mu times the derivative of h with respect to t. And furthermore, because it becomes spatially varying, when you take, what you're going to do is take another curl of this and stick it in, or I'm sorry, take two curls of this and we're going to take this and stick it in here. Then all of a sudden the number of derivatives gets very large. It becomes very hard to manage. I'm just going to tell you it's not as simple as I'm making it out. If the value of mu or epsilon or sigma is a function of the magnitude of the field or is a function of you might say the rate of change. And I don't want to go there right now, but these things can get really outlandish, and especially when they have very high power applications. So just keep in mind what I'm trying to tell you is something that you just keep in the back of your mind when you're doing these on the job. This is standard though. Okay. Now, what is displacement current? This is it. This is displacement current density. You can just call that J displacement. What it does, and the only thing it does, is makes that curl of H equation true for time varying and non-time varying effects. That's the only thing it does. So the way the book will talk about displacement current almost all the time is try to give you a handle on what it really means. This is displacement current density. The units have to be the same as J over there. They're amps per meter squared. Y'all with me? And here's the thing that troubles. So if you look at a capacitor, let's just assume we have the area of the plates A, separation distance D, and just make this epsilon naught. So it's air. And then I put a voltage here, and I'll just make this say Vs equals, say, or I'm going to do this. I just say this is going to be some V0 cosine of omega t volts here. You with me? Now, there's a capacitance that this thing, if it's parallel plate and this separation distance d is small, we're assuming d much less than square root of area. Square root of area is proportional to the dimension of that plate if it's a square plate. So d is very close. That means the capacitance of this thing is about epsilon naught area divided by d. Go with me? Now, when you were taught about capacitors, you learned that if you just had a voltage plus or minus V of t here, and you had a capacitor C here, that the actual current that would drive through here, the I of t, would be simply C times dV dt. Y'all remember that? Or not?
Yes.
So it's dependent on the time rate of change of the voltage. So if this is a DC battery, there is no current. I want you to hear me on this one. It's real important you see this. Does any real current come from this plate that's accumulating positive charge and this? Does any real current flow from here to here? No. Well, what happens? Real current flows here, right? It flows there because that is a conductor and it's going to cause charge to accumulate there. And real current's going to flow there, but in between there's no real current. We call that current between these things I displacement. It is not real charge moving from top plate to the bottom. It's inducing charge in the plates because of the voltage. That's all it is. The charge can't move any further. So when we talk about I displacement, what is it? Well, I displacement is the current density. It's just JD times the area of the plate. Y'all with me?
Yeah.
The displacement current. So now this gets this become obvious. All right. So let's go back to this. How would we calculate dD dt there? I'm going to expand this capacity. You're going to see this in a heartbeat. Watch. I've got a distance d, right? And I got a voltage difference plus to minus V here. Just go with that. You okay with that?
Yes.
What's the electric field in here? We're assuming planar, and we're assuming a small separation compared to here. Well, it's just the voltage divided by D, isn't it, class?
Yes.
All with me? That's the electric field. What's the D field here? Well, the D field is just epsilon E, right? Or it's epsilon times quantity V over D, right?
Yep.
And what's the displacement current density? The derivative of this. So JD is really going to be equal to, in this case, it's going to be epsilon over D times dV dt. All right, this would be the density. And what's dV dt? Well, I give that as, what do I give it as? V naught cosine of omega t. Then this becomes epsilon, whatever it is, epsilon naught over D, whatever D is. dV dt becomes simply, if it's a cosine omega t, derivative of cosine is going to be sine, right? Mm-hmm. And it becomes simply omega times the sine of omega naught t, and that would be JD. And you can see it's dependent on omega. Yep.
Would there be a negative part in there?
Well, I'm saying this is the direction. If you had that as positive, you could put a negative there. But the real deal is that's what JD is. Now, that's all it is. It's sort of a way to explain what happens in the dielectric. There is no real current that flows, but there is this, quote, displacement current that allows us to think of a continuum of current flowing in there. All right, now, problems. So if you can go to that section on displacement current density that you were looking at, can you give me, right here, give me the first one, or no, yeah, we can do the first one. Give me a second to erase this. Is there a test in here or anything?
I didn't have any tests.
Well, I understand if students want to stay home, that's, I can understand that because you're recording. By the way, thank you so much for recording. I understand that in a way. But I do appreciate you guys coming. I want to tell you one other thing. It's much better to come in person than watching lectures online, in my opinion, as far as your ability to understand something. You can ask questions whenever you don't understand something. Go ahead.
The first two are just making sure that divergence is equal, the vector field is 0. Do you want me to do the first actual?
No. The divergence of B is 0. Divergence of, it's got an A or something, right?
Yep.
You want to take the curl of A to find B. All right, go ahead.
So you want me to do the first, not that problem?
No, don't do where's the first displacement current? The section is displacement current.
Yeah. A pair of
Which
6.
number?
This is 524.
Go ahead.
A pair of 60 centimeter squared area plates.
Cubic centimeters. So we got area equal to 60 cm squared, which is really going to be, this is going to be 60 times 10 to the minus 4 meters squared. Go ahead.
Is separated by 2 millimeters.
So D is 2 millimeters. Go ahead.
Sorry, I'm also writing this down. And there is an ideal dielectric characterized by epsilon relative is 9.
Okay, good. What's it?
The voltage is equal to 1 sine.
Voltage is what?
The voltage is 1 sine, or I guess just sine, 2 pi times 10 to the third
T.
t.
Volts, right?
Yes.
Okay. And what do they want?
Find I displacement.
Displacement current.
Find the current.
Yeah.
All right, so it's connected. Guys, this is about as simple as it gets. Here's VFT. You don't need, I'm leveling it, you don't need to do this in the differential form. They want the current, right?
Yep.
Do we have a capacitor there, people?
Yeah.
All right, so the way you would do it, because you guys are smart, go ahead and put the voltage source here. That's equal to just sine, and I'm going to call it of omega t. Omega here is 2 pi times 10 to the third, right? And that would be in radians per second. Next, I'm going to put the capacitance here, and the capacitor value here is simply epsilon A over D. Here, epsilon relative is, what did you say it was? 9. So it's 9 epsilon naught area. It's 60 times 10 to the fourth, or 6 times 10 to the minus third meter squared over distance, which is 2 millimeters. That's 2 times 10 to the minus third. And that means the capacitance is 9 epsilon naught. And it's going to, minus 3's cancel, times 3, or it's 27 epsilon naught farads. Y'all with me? I'm just going through the math on it, right? Now, they want the current through here versus time, or they want a magnitude. Can you tell me?
They want to find determine the displacement current. That's all it says.
All right, I mean, just in time, or they want to?
It doesn't
It just
say.
says determine the
All right, well, if you wanted it in time, what would you do? If I wanted this, which is I displacement, if you want the whole thing, you'd say I displacement itself is equal to C times dV dt, right? We got the capacitance, it's 27 epsilon, right? Epsilon naught, pardon me. dV dt is going to bring an omega out, so you're going to get omega here, and it's going to be derivative. Take a look at this. Derivative, I think I did that wrong last time for cosine. Be minus this. Derivative of sine is going to be, really going to be omega times cosine, right? Of omega t. And that means the capacitance itself, so I have 27 times epsilon naught, and then I have times omega, which is 2 pi, times 10 to the third. And it would be times the cosine of omega t, so we can get the magnitude right here. What is that going to be?
I can do it real quick.
Epsilon naught, you can use 8.854 times 10 to the minus 12.
12 times 2. It's gonna be 1.5 micro.
I have the same thing.
Microamps
Yeah.
times the cosine. What does he have in the answer?
I don't know. What's the number? What's the
524.
24.
Cosine, and then I guess you can just sub W back in.
That's where you go.
1.5 micron?
Yeah.
Here's the tip, if you really want to do this, and you want, I'm worried about peak current, just make this capacitive reactance 1 over J, it's, capacitive reactance is going to be 1 over J omega C. Just make this 1 over J omega C, divide that into the voltage you get. You get the magnitude. You all hear me on that?
Yeah, it's
So it's easier that way, instead of writing out the cosine, doing the derivative. You got another one?
sure, we can do another one.
How about you got it? Yeah, go ahead, find. Yeah,
We can do 526.
But this is,
Almost.
in my opinion, this is, these are trivial.
Problems.
What? What does he say?
There's only 3 actual problems on this.
I mean, is there anyone that
Gave more problems.
Was that the last problem then?
No, there's
No.
2 more. There's 2
There's
on
5,
vector
but 2
fields
of them
and
are
3 on
stupid.
actual displacement current.
All right, hold on. By the way, for B, you just take curl of A. He has a magnetic vector potential. We'll talk more about an EMAG 2 and stuff, but okay, for this one, what is it?
Let's do 26.
What is it?
Yeah, I think 26.
We have a 1 meter
26.
coax.
It's just 26?
Yep.
5-26. Go ahead.
Yep.
We have a 1 meter coax.
Long coax or
Yep.
what?
1 meter long coaxial cable of interconductor diameter 2 millimeters.
Diameter?
Yeah.
2 millimeters.
And outer conductor diameter 6 millimeters.
Oh, okay, so diameter 6 millimeters, called the outer 6 millimeters. Go ahead.
With an ideal dielectric, epsilon relative equals 10.2.
Okay.
A voltage, V of t equals 10 cosine, and then bracket 6 pi times 10 to the 6 t millivolts.
It's 10 to the 6 T.
No, it's 6 pi times 10 to the 6 t. 10 to the 6 t millivolts.
And then what the current?
It's millivolts, and then
Millivolts. Huh?
yeah, displacement in the conductor, blah blah. Neglecting fringing fields. Find the displacement current between the inner and outer conductors.
This is an no-brainer. We just need to find the capacitance, just like the other one. You all with me?
Yes.
How do we find the capacitance? Well, I don't know if you guys remember, but we get capacitance problems, right? You assume a charge, put it on the inner one of a certain length, then you find the D field. That's charge, which is Q over 2 pi. It's going to be Q over 2 pi rho would be the D field. Multiply that by epsilon. Then you got to do what? Yeah, the E field.
Then
multiply
find the
by
voltage.
divide by epsilon. Pardon. Then integrate it, right? You're going to get a natural log. Now, at the end of the day, after everything is said and done, you get a capacitance equal to, it's a length of 1 meter, right? It's going to be what? That's going to be, remember? 2 pi epsilon naught epsilon relative over natural log of B over A. And this would be per meter, but since it's only 1 meter long, that would be the capacitance. Does anybody remember this? I kind of babbled it. Kind of through how
I do remember doing this.
you just
Yeah.
assume charge.
That's just the final result.
All right, then you find the D field, charge over 2 pi rho. Then you find the E field, multiply or divide by epsilon. Then you go ahead and find the voltage, integrate, right? Then you take Q over V is C, and this is what it comes down to. Now that's it. So they want the current, right? If that's the capacitance, how do you get the current? Can't we just write this voltage right here as just 10 at an angle of 0 degrees? I'm going to do it the way I would do it in the real world. I can say, we'll do it in the phasor. This is really 10 at an angle of 0 degrees volts. That's a peak value. Now I put the capacitor in here, but instead of putting the capacitor, I'm going to put the actual capacitive reactance. Capacitive reactance is minus J over omega C, right? Omega here is this, right? Just watch this. Y'all with me? That's omega. Can you all follow me on this, guys? Now, I'm just doing it the way you would do a circuits problem. So this current, they want the current, right?
Yep.
My displacement is going to be 10 divided by this, or it's 10, and I can do it this way. It's 10 divided by that, it boils down to omega times C, and you can see, I'll put the J down here, so you can see it's 1 over that. And you go ahead and divide that by this, the J comes upstairs. So this will be the magnitude of current at an angle J, which is 90 degrees, which is going to be 10 times omega, which is 6 pi times 10 to the 6, and times C. Can you tell me what this is? You got the, now remember, the ratio of diameters or radiuses will be the same, right? So this is going to be 6 over 2, or it's log 3. So this is 2 pi epsilon naught, epsilon rho is 11, or is 10.2, right? Over the natural log of 3. Can you give me that?
I got 50.6 picofarads.
Okay, I may be right. Small, to say the least.
Oh, but I forgot to multiply by epsilon relative. So
Take that times 10.2, so it's going to be 506 picofarads. Right? Well, more than that. 510 picofarads.
it's 516.
516 picofarads, okay. And then come over here. So what's your current going to be? It's going to be J times 10, right? And there's a C there times 6 pi times 10 to the 6, and then it's going to be times 516 times 10 to the minus 12. And you guys can give that to me?
I got 97.3 micro.
J 97.3 microamps. Now that J just means one thing. You can add 90 degrees to this, right? You could take 6 pi times 10 to the 6t, cosine of 6 pi times 10 to the 6t, multiplied, and then add 90 degrees inside that cosine argument, or you could turn it into a sine, either one.
Sorry, milli, not micro.
Milli. All right. What does he have?
Negative 97 micro.
What? Say again?
Yeah, negative 97 micro.
It's because the voltage is in millivolts, and that's why it goes to micro in the end.
All right. So it goes to micro.
Oh, so it should be micro because we multiply by 10 millivolts.
Right.
Okay.
So this is microvolts because this is millivolts here. Okay, that's right.
Microamps.
Microamps. Pardon. That's it. That minus sign that he has, it depends on how they designate current direction. Just remember, the voltage of the current will be 90 degrees out of phase. Have you ever heard Eli the Iceman? Anybody?
I've heard that. I don't know what it means.
Okay, here's what it means. And this is an old thing. They used to have all sorts of different ways to remember voltage and current relationships. First I'm going to put down Eli and then Iceman. Okay? So L is a symbol for inductors, right? And what they're going to say is, on this one, the voltage here on an inductor is going to lead the current by 90 degrees. So it means the current here is going to lag by 90 degrees. Here, Iceman, the C means capacitor. That means the current will lead the actual voltage by 90 degrees. You all know the difference between lead and lag, right?
Yeah.
All right, so that's it. In capacitor, the current's always going to be ahead of the voltage by 90 degrees. And for an inductor, the current always lags behind. So when you have a transient on an inductor, say put a voltage on it, the current, just as that transient happens, is 0. It's going to start going up because you can think of the inductor as something that requires like momentum to get current through it. For a capacitor, it's the opposite. As soon as the voltage is felt, it dumps tons of current through it. All right? And that's what goes on. But a capacitor, as time goes by, it looks like an open circuit, and an inductor like a short. All right, that's the way, the reasoning behind it. Okay. Is there another one of any difficulty in that? I don't think so.
It's the only other one. Yeah.
What is it?
plot the loss tangent of seawater, it gives you sigma and epsilon relative,
All right.
versus log frequency of 1 hertz.
So I need to talk about loss tangent. Now, this is in his book. Let me see for a second. And I want to tell you, it's not a big deal, but this is something you might as well get exposed to, I think. Where the heck is this loss tangent? And it's kind of important. I should do this. It's not that important. Well, it's important. At least this has a way of dealing with loss. Where's this loss tangents?
Oh, there it is. That means.
Yeah, but he doesn't have the good one here. This is. I'll talk about that next time. Loss tangent is something. Hold up for 1 second. That in general, in the second half of this course, we talk about it. It's relating. It's a way of describing the losses inside a dielectric, and that comes later, really, than in this section. And he'll go through it in a lot more details. But before I get off topic, I've got a minute, no, maybe 2 minutes, I think. Is that right?
Yeah. You have 2 minutes.
I probably owe you time for all the times I've held you over. Here's the deal. For class on Friday, quiz is going to be on that section we just covered, 5.3 and 5.2. In other words, think about divergence of J plus d rho dt equals 0. Think about the charge problems we did, right? Charge decay. Think about the problems with induced EMF and all that we went through. Okay? And I'll give you some more homework, and I'll give you a I'm not going to put you a transformer problem on Friday. I won't. And thank you. I owe you, as usual, time. Any other questions or thoughts? You got to run to a bus.
Yep.
Did you check any of those games out that I mentioned?
Actually, I didn't have time. But I will get back to you on Friday because I have a lot of time tomorrow. So.
All right, you take it.
Thank you.
Guys, where's that guy? His legs busted, Sam? I mean, he's in